going to talk about a different area today. I'm going to try to get some different topics. Today we're going to be talking about something called optimization and linear programming. How many people are familiar with something called linear programming? Have you heard of it? Not so much. Okay. Actually, it's a very big study in mathematics and in algorithms. Optimization using linear programming approach. And there we go. So linear programming approach is based upon solving a set of simultaneous equations. That's good. Okay. So if we have one equation in one variable, we can solve it, right? Okay, so we have one variable. So for example, x squared is equal to x minus 5. We can solve it, right? Mm-hmm. How do we solve it? Well, it's a quadratic equation. You can probably quadratic formula. Find out two solutions. If it's a linear equation, we have something like 3x is equal to 5. So we're just going to divide everything by 3, find out the value of x. But if we have two equations, for example, 3x plus y is equal to 8, and 2x minus y is equal to negative 4, then we have two equations. But we also have two variables. So if we have an equation, for example, like 3x plus 5y is equal to 10, you cannot solve that equation by itself. Why not? Because for one value of x, you can find a y. For a different value of x, you can find a different y. So for an infinite set of x's, you'll get infinite number. We have no one single solution to this. But if we have two equations and they have two variables, then what we can do is we can solve them by using a technique called simultaneous equations. If you have this, some x's, some y's equals a constant, some x's, some y's equals a constant, we have an equation where these two are equal and these two are equal. Right? So we're going to add these two and get some value. We're going to add these two, get the same value, so we create a third equation. And so our goal is sometimes to add them so that we cancel one of the variables. You guys are familiar with that? And so the mathematical technique for that is usually referred to as Gaussian elimination. Have you heard of Gaussian? How many people have heard of Gaussian elimination? Only two fans of Gauss. Nobody else knows anything about Gauss. So I'll show you a little bit about how it works, just so you can. Now, you know that if you have two equations and two variables, you can combine the equations. So, and sometimes you may find that you have, now, when you have an equation in two variables, okay, what is that an equation of? Well, if you have, for example, if you have y is equal to 3x plus b. So you can say it's going to be 3x minus y is equal to minus b. So you have two variables, and you have, so that can be describing a linear equation, correct? Okay, so just show you a very simple thing, and then we're going to get into the approach here, just in case you don't know some of the basics here or forget about them. Okay, so I have how many equations? Two equations, how many variables? Two. Okay, so what we want to do is some particularly difficult equations. what we're going to do is basically we want to solve now, these are equations of lines. These are equations of lines. So basically, we're looking for a single solution of x and y. And when you were talking about a linear equation, an x and y is a point in a plane. So if there's an x and a y that satisfies here and also satisfies here, then it's a common solution. And with these two lines, it's the point of intersection of two lines. But in some cases, the lines don't intersect, the lines are parallel. In which case, what's going to happen? There will be no solution. Okay? And in other cases, we may have an infinite set of solutions, and that happens when? When the lines are coincidental, and that means when the lines are the same line. Because you can have two equations for the same line that look a little bit different, but actually are the same equation. Okay, so what we want to do is we want to solve for x or for y. You can see here that what can we do? We can add the equations together. If we add the equations together, we're going to get 7x plus 4y is equal to 11. So we get 7x plus 4y is equal to 11, right? Does that help us? So now we have three equations in two variables. What we really want to do is we want to cancel one of the variables. We want to cancel one of the variables. So to do that, so this is nothing wrong with what we did. This is okay. But what we want is, for example, let's say we wanted to add these equations. If I added them, we got a bad result. Not a bad result, but not a helpful result. How many times 3 is 7? 2 times 3 is 6.
One remainder.
So 2 and a third. And 2 and a third is 7/3. Right? 7/3. So what I'm going to do is I'm going to take the equation number 2, this is equation number 1, number 2, and I'm going to multiply equation 2 by 7/3. So, what is 7/3 times 2?
14 by 3.
14
Over 3.
over 3, x. What is 7/3 times 3? There's a minus here.
7.
Minus 7y. And what is 7/3 times 15? Well, 15 over 3 is 5, so it's going to be
5, so 35.
So now we have equation number 3, right? So what we want to do is we want to solve the equations, and we notice that if we look at equation number 3 and equation number 1, we have 7y and negative 7y, and now if I add those together, I'm going to get what? I'm going to get a cancellation of the y's. So in this case, if I add these equations together, I'm going to get 0y, and then I'm going to have negative 4 plus 35 is going to be 31, and then I have 5x and 14/3 x. Now, 3, 6, 9, 12, that's going to be 4, which is going to be 9, and how many thirds? 2/3 plus. So that's going to be 27, 29 over x, 29 thirds times x is equal to 31. So x is going to equal to 31 times 3 over 29. Right? Let me know if I'm making a mistake. And that's going to be 93 over 29. So that's the value of x. How do we find the value of y?
Substitute the value of x in an equation.
The value of y we can find by now taking the value of x, plugging it in here, and that becomes a constant, and then putting this on this side, dividing by 7, we have the value. So we eliminate one of the variables by canceling it from two different equations. And that gives us a one equation in one variable. We can solve for one variable. Then we go back to the two variable equations, substitute, and then solve. Okay. All right. So let's take a look at linear programming idea. So we're going to borrow from this idea. So linear programming is an optimization technique involving a set of variables related by mathematical equations or sometimes relations, and these relations are referred to as constraints. So what we have is we have the following function. So the function is, rather than calling it x and y, we're just going to call it x1, y1, x1, x2. So that becomes the first. And the reason we do that is so that we can extend it to x1, x2, x3, x4. We can extend it to not just two-dimensional objects, but three-dimensional objects, four-dimensional objects, and any dimensional objects. So we want to maximize x1 plus x2. But of course, since if we don't have any limits on x1 and x2, you cannot maximize it because you can just let it go to infinity. So what we're going to do is we're going to have some constraints. The first constraint is going to be that both values have to be non-negative. So that's what x1, x2 greater than or equal to 0 means, non-negative. If you think about it in the space of a Cartesian plane or a plane, that means that they are in which quadrant? Quadrant number? They're basically going to be housed in quadrant number 1. Nothing will be in 2, 3, or 4. So they'll be in the upper quadrant to the right-hand side. Okay, the other restrictions we have is that we have to have minus x1 plus x2 must be less than or equal to 5. Well, again, if we look at this equation, we can represent this equation as a line. And if we think of x1 as x and x2 as y, this would be something like y is less than or equal to x plus 5. And x plus 5 is a line with a slope of 1 with a y-intercept at 5. So we can imagine what that line would look like. It cuts at the 5 on the y-axis with a slope of 1. And it just goes on like that. But because it's less than or equal to, it means all the space under that line. So that defines, the inequality defines what we call a half plane. Not just a line, because it's not equal to. It's a half plane. It's everything underneath that line. And if you look at this one, this is x1 plus x4, x2, less than or equal to 45. Same thing. We can say this is going to be 4y is less than or equal to negative x plus 45. Negative x plus 45 means that we have, and we divide by 4. 45 divided by 4 is going to be 11 and a quarter. So that's the y-intercept. Slope is going to be negative 1. And less than that means everything below that line. So what we're doing is we're basically shading a bunch of half planes. We're shading them in a way that's going to define a region. And that region will be what we call a convex polygon. Convex polygon. It means it's always going like this. It never has an in position. That means that no line can cross in and out of the polygon. You can only cross into it and then out of it. Never again are you going to enter into it. It's a convex polygon. Okay, so if you look at these lines, you can imagine that they will look something like this, graphically speaking. And so you can see this is the one that cuts here at the point 5 with a slope of what? What's the slope here? 10 minus 5 is 5. 5 minus 0 is 5. That's a slope of 1. That's the line we're talking about. So when something is less than this line, and this is what we were talking about, this one right here, y is less than or equal to x plus 5, we're talking about everything underneath this line. So as you project this line here, it's all this stuff in here. But this is the other line we're looking at, which is this one right here. So notice that that's going to be someplace up here is going to be the y-intercept, which I think was something like 11, I think, or something like that. I forget exactly what we figured out. So if you keep this, if you consider this as a y, it's going to be minus x, so it's a slope of minus 1, but when you divide it by 4, the slope is minus a quarter. Okay? So therefore, I can extend this line, and the solution for the inequality is going to be everything that goes underneath this line. But because we have multiple constraints, specifically under this, under this, under this, and under this, basically this is going to be here, and we have them in the first quadrant, then this second quadrant, third quadrant is ruled out, and we have in fact defined a convex polygon. So now what we're trying to do is we're trying to find the maximized function. The maximized function is x1 plus y1, or if you want to think of it as x plus y. We want the biggest value of x plus y. Well, if you stop here, the value of x plus y here is 5, because it's a 0 plus 5. This is a 15, this is an 8. Okay? This is a 15 also, 5 plus 10. So we can visualize optimizing this function by looking at what the optimal function looks like. This function basically, in order to optimize the function, what we're doing is we're saying we want this function to have the highest possible value of x plus y. And what that means is that x plus y is equal to c, where c is the maximum possible value. So we can solve this equation for y and look at the fact that this actual optimizing linear equation actually is also can be written as y is equal to minus x plus c, right? So this maximizing the value of c. So assuming that the c exists, then x plus y is equal to c is the line y is equal to minus x plus c, which means that this is the line of a slope of -1 plus a constant. So if you imagine a line of a slope of -1 like this, and this is, let's say, the y-axis is right here, you can imagine this line is coming up from infinity, go very, very high, until it hits our convex polygon, also known as a simplex. The convex polygon, we call it a simplex. So as this line is coming, it's going to hit it like this. If we want to maximize the function 2x plus y is equal to c, then we would get y is equal to minus 2x plus c. That would be the line coming from up high at a more sharp -2 slope. Okay? Does that make sense? So this is dividing this. If you had another, for example, let's say we want to maximize the function, for example, 2x plus 5y is maximized at c, then you would have y is equal to minus 2/5 x plus c. Right? So that line would be coming in from very high above, trying to hit the simplex. Wherever it hits the simplex, that's actually the point that maximizes the function. So that's our visual here. So therefore, each inequality represents a half plane in which any solution to the linear program must lie. So they are defining this closed space, this closed simplex. A point within the region maximizes the objective function. The region is defined by the intersection of half planes, is always going to be complex, and we refer to this as a simplex. And here you can see this imaginary line coming from way up high, and as we are sliding this line lower and lower and lower, it's going to hit the simplex. You can kind of see, since this is scaled properly, you can see that that line is going to hit the simplex where? It's going to hit it at an edge, or at a point here, at a connecting point. So therefore, we expect that possibly our maximized value will be at 9, 9, and what that means, it's going to basically be 9 plus 9. Notice that if this line had a much steeper slope, for example, if the slope was minus 30, the line would be almost like this, and so it would more likely would hit over here. Okay? And if it had a much more gentle slope, it might actually hit this point. If you tilt the line here, it would hit that one first. So we can solve this simplex, and it's a two-dimensional simplex. But the simplex can actually go into a third dimension, okay? So for example, we're going to add the simplex and go into 3 dimensions, but we're going to try to modify them as little as possible. What we're going to do is we're going to add another variable. We're going to call it x3. So now we have x, y, and z, or x1, x2, x3, whatever you want to think of it. So now, geometrically speaking, we're talking about dividing our space into half spaces. Instead of having half planes defining a 2-dimensional simplex, we have half spaces defining a 3-dimensional simplex. So it becomes a little bit more difficult to imagine, and certainly we can go to 4 dimensions or n dimensions, and then we lose the good ability to have a really good geometrical visualization, but it may make a lot of sense because it's easy to understand that you might want to optimize an equation with 4 variables. Very common, right? You want to maximize some bunch of these variables together according to some constraints. So what we did here is basically I added the third variable, but if you look over here, I did not include the variable here, or here, or here, or here. So these equations stayed exactly the same as in the 2-dimensional simplex. But I added one more constraint, and that is x3 is less than 4, but still non-negative. So what's going to happen is, if we look at my simplex here, the simplex now is 2 dimensionals. There is no third dimension, but now we've added the third dimension. That third dimension allows us to come right at you. Okay, so these points can go from 0 on the z-axis, if you will, up to 4, up to 4, up to 4, 4, 4. So basically what we have is we have another copy of this 4 units away, and it looks, that's our half space. Okay? That's what it looks like. But the shape is exactly the same, and we don't have to worry about any kind of crazy angles, so that kind of simplifies things. So we'd like to solve this one, so you can see what the 3D simplex would look like. So this is the original in here. These are all the original points we have. All the ones that have a 0 here are the original points, okay? And all the ones that have a 4 are the new points. So this is basically, this is the simplex up to here. Makes sense, right? So inside here is the half space that we're trying to optimize. So now we're trying to optimize between A plus B plus C. Now we could be, we're optimizing x1, x2 plus x3, but we could be also optimizing 2x minus x2 minus x3. So there are many things we can be optimizing. But these are linear optimizations. So this works on, that's why we call it linear programming. Because the equations are linear. What does linear mean? First degree. That's linear complexity, right? N to the first power. All right, so that's what it is. So how are we going to solve it? So we're going to solve it by using this technique of Gaussian elimination. And what we're going to do is we're going to rewrite our inequalities, which are here, as equalities. So, for example, now if this says x1 plus 4x2 is less than or equal to 45, I cannot just say equals to 45, because that's not true. So what I'm going to do is I'm going to say x1 plus 4x2 plus some variable k is equal to 45. That variable k is non-negative. That's a constraint on that variable. Does that make sense? If that variable k is non-negative, that means it's 0 or higher. If it's 0, then it could equal 45. If it's higher than 0, then this value will be bigger with k. That means it's going to be smaller without k. So the k becomes a special extra variable, which is not part of the original problem, but we do it because we want this variable to be non-negative and allow us to change the inequality to an equality that we can solve using Gaussian elimination, kind of like what we did before. Multiply this equation by 3 sevens everywhere so that we can cancel or something like that. So that's what we're going to do. Now, x1, x2, and x3 are called variables. since we're going to be adding more variables for each inequality, to turn each of them into an equality, we have to add a variable into each of them because they're all different. And so we're going to call those variables slack variables. S-L-A-C-K, slack variables. Slack variables are those non-negative variables that turn inequalities into equations. And so this is what we're going to get here. And so now you can see the slack variables here. So our minus x1 plus x2 less than or equal to 5 becomes minus x1 plus x2 plus y1 is equal to 5, where y1 is a slack variable, which is non-negative. Does that make sense? So as long as y1 is non-negative, our equation is correct. We don't care what y1 is as long as it's non-negative. And the same holds true for y2, y3, and y4. Okay, so we've introduced 3 variables. Now we introduce an additional 4 slack variables. All of them are constrained to be non-negative. And the reason they're non-negative is so that when we add multiples of something, we know we're increasing, and when we subtract them, we know we're decreasing. That's the reason for the constraint. Because we're going to be adding multiples of things. If we add multiples of things that are positive, we're increasing. So we have, at this point, 1, 2, 3, 4, 5. 5 equations, n, in 8 variables, m. And the 8 variables are all the x's and all the slack y variables. Since m is greater than n, we assume that there are many possible solutions. We need to find the one that maximizes the objective function. We don't care about the value of the y's as long as they don't violate their constraints. We do care about the values of the x1, x2, x3 because they will give us the maximum function. This is just telling you how you can work with negative variables. I'm going to skip that for a second. Okay, so what we're going to do is we're going to create a matrix. And this matrix is going to contain, for each variable, it's going to have a row. So this is corresponding, this row 1 corresponds to x1, this is x2, this is x3. There are only 3 variables, but we also have y1, y2, y3, y4, y5. So x1, 2, 3, y1, 2, 3, 4, 5. And this is the value of the equation. So we write the equation basically. This means minus 1 x1, minus 1 x2, minus 1 x3. This is minus 1 x1 plus x2 plus y1 is equal to 5. That's the translation of that equation. The bottom one says what? This says x3 plus y5 is equal to 4. So you understand what it is. Now I only have 5 equations. 1, 2, 3, 4, 5, which correspond to the rows 1 through 5. But the last one here is something I don't have at all. This is something I just added for the process of this linear programming problem. And that is, we're going to put in the opposite of the sign of the variable that we're trying to maximize. So we're trying to have x1 plus x2 plus x3 maximized. So we will do minus 1 for x1, minus 1 for x2, minus 1 for x3. If we're trying to optimize the function x1 plus x2 plus 10x3, we would have minus 1, minus 1, minus 10. So we will always put the opposite signs. If we're trying to maximize x1 minus x2, this would be minus 1 plus 1. Okay. Now, so what you will do is to start this process, you will put simply the opposite of the signs of the variables that you're trying to maximize. Notice that the slack variables do not get entries because we don't care about them. All we care is that they don't violate any constraints. Now, what we're going to do is we're going to pivot this and trying to solve it. And it looks complicated, but the goal is we're trying to only have one equation have the value of x1. Remember how in a problem underneath the board we basically added those 2 equations? So what happened was, in that third equation, the equation that we produced by adding 3/7 of one other equation, we produced another equation that basically only had variable x, but didn't have the variable y. Well, here we have x1, x2, x3, so we want only one equation that has the variable x1, only one equation that has x2, and only one equation that has the variable x3. So if you have the variable x1, you must have some type of a number here in x1 column. But everybody else has to have a 0. Everybody else has to have a 0. So for example, if I want variable 1 to appear in equation 4, then I have to divide equation 4 by what? If I want to have a 1 here, because I want to know what is 1 times x1. In order to do that, I have to do what? I have to divide this equation by 3. And that will give me 1. Then I have minus 4/3 plus 1/3 y4 is equal to 8. Okay? So that's going to be our goal. So what we're going to do is we're going to be doing something called pivoting. Okay? So, and again, the reason we have the number of equations is n plus 1 is because we have 5 equations, but we add the optimizing equation. And the reason we have one more in terms of columns is because we also have the value of the equation on the right, and that's why it's n plus 1. So now we're going to do this Gaussian elimination by pivoting the matrix for P and Q, where P is the matrix row and Q is the matrix column. So for example, let's say, so my goal is going to be putting a 1 into every place where I want the variable to be, and a 0 where I don't want it to be. So if I want to solve for the variable x1 to be in equation 3, then I must end up with a 1 here, and I must end up in 0 every place else. But specifically, in order to get a 0 up here, let's look what I have to do. Let's actually use a different one here. Let's say I'm going to use this 3 here. So in order for me to get a 0 here, to get a 1 here, I divide by 3. But in order for me to get a 0 here, I cannot add this equation to this equation. This is the P value, this is the Q value. I'm pivoting for P and Q, which means I want a 1 here, I want a 0 every place else. The way I'm going to get a 0 from this 3 is I need to add what part of this equation to this equation. I cannot add this equation to this equation, but I have to add what part of this to here? 1/3. So 1/3 of 1 would be 1. If I added that, 0. So that's a good thing. Now here I have to basically add what? 1/3 of this to this. So all I care about right now is just changing, so I add a 0 here. Now I also will add 1/3 of this to here. I will then, what am I going to do here? I'm going to add negative 1/3 to here. That's going to give me a 0. What am I going to do here? I'm going to add a negative 2/3 to this equation. And that will make it a 0 here. And here, nothing to do. So you understand how I can do this pivoting, right? So I will choose how to eliminate each one of the numbers that I want to go to 0 by selecting some row. So if the row is 3, I'm going to add 1/3. I'm going to get 1/3. I'm going to add negative 1/3 because it's a positive 1, so I got to subtract 1, right? That's a negative 1/3. So basically, I will have a different coefficient for each of the equations I'm eliminating. Okay, so what we're going to choose to do in this case is we can arbitrarily choose to do something. And we're going to pivot P equal to 4, Q equal to 1. P equal to 4, Q, we're going to do it right here. So look at a couple of things that you're expecting. Because this is a 3 and you got to get a 0 here, you got to take 1/3 of this and add it. What's 1/3 of negative 4? Negative 4/3. What's negative 4/3 plus negative 1? Negative 7/3. So you expect to get negative 7/3 here, and that's negative 7/3. Right? 3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Okay. And when you come here, you're going to take a third of that, and you're going to add it here. What value are you going to see here? What value you expect to see here? You expect to see 0.33333. And what value do you expect to see here? 8, because a third of 24 is 8, and you're going to add it to this equation. The value in position row equations 0, position m plus 1 is going to be the value of the optimized function for the variables that are in the solution. So basically, when I do this, my value in a sense is going to be 8, and you'll see this in a second. So you can see over here, this is the negative 7/3, this is the 0.33333, this is the 8. So you can see how this equation was flattened to get a 0. Now the same thing happens here. In order to get a 0 in this equation, we had to also take a third of this and add it. So that's going to give me a 0. Now what do we do here? A third of that, what's a third of that? Negative 4/3 plus 1. So it's negative 1 1/3 plus 1, it's going to be negative 1/3. So we flatten that equation. Here's a negative 1/3. And notice what happens here. And then what do we do here? We have to choose another constant for the equation number 2. We have to take a third of that, but then opposite of that. So what's a third of that? A third of that is going to be negative 4/3. Opposite is positive 4/3. So 4/3 plus 4, 5 1/3, right? 16. Yeah, 16 over 3, and there you have it. So where is it? There it is. That's 16/3. It's 5 1/3. So do you understand what we did? You understand how we got all those zeros here, right? So we can't just change this one. Whatever we do to make this happen, it affects the rest of the equation. So our objective function right now is equal to 8. Now, here's the important thing to see. There are two, we can divide our variables into two categories. Of course, one of them are the real variables, the other one are the slack variables. But when we're doing a solution using Gaussian elimination, some variables will be referred to as the bases. Those are the variables that are part of the solution. And the other ones that are not part of the solution are called non-bases. And the bases, non-bases has nothing to do with the real or slack. It just means, are they in the solution or are they not in the solution? If they're in the solution, that means they're the only ones that appear in the solution. If you look very carefully, that after doing this elimination here, we see that we have a value of 1 times x1, right? And the value here is 8, but we still have minus 1 1/3 times x2, and we don't have a value for x2. In order for us to have a value of x2, we must have only one equation with a 1 here. So we're going to try to do a next pivot. So, basis variables are variables that correspond to a solution represented as a column with a single 1, all the rest zeros. So because we have a 1 only in one of the columns, and the column is the x1 column, we say x1 is in the basis. x2, nope. x3, nope, because we got that. So therefore, x2 and x3 are not basis. y1, y2, y3, and y5 are in the basis, but we don't care about them. Only when a variable is in the basis do we look at its value. As long as it's in a non-basis, we don't care about its value. So, and this is the objective function. So right now we're saying if you make x1 8, you will have an objective function of 8 because the variables are assumed to be non-negative. That means it's going to be 8. Why? Because then the other ones can be zeros. That's the smallest values we're going to have. Okay, so now we're going to pivot for p equals 3 and q equal to 2. 3 and 2. So this is a crazy variable, 3.67. We need to turn this into a 0. So this is basically, this is 3 2/3, which is 11/3. And this is negative 7/3. So we have to take a fraction of this to make 7/3, add it to here, and do the same fraction continuously here. So let's see if we can figure out what it's going to be. So what part, so this, how many thirds is this? 11 thirds. 11 over 3, and this is 7 over 3. So 11 over 3 times something is going to be 7 over 3 times x. Right? 11 over 3 times x is 7 over 3. So x is going to equal to 7 thirds times 3 over 11, which means it's going to be 7 over 11. But specifically, because the sign is positive, we can just multiply by 7 over 11. If it was a negative 3.67, we'd have to multiply by a negative 7/11, right? So when we multiply this by 7 over 11, we're going to get what here? And add it. Multiply this by 7 over 11, add it. We'll get 0. When we multiply this by 7 over 11, we'll get what? We will get 15. Because it's going to be 19, right? Because it's going to be 7 over 11. It's going to be 7. So we're going to add this to 8. It's going to be 15. So our objective function will go to 15 as x2 enters into the basis of the 1 here and all zeros every place else. So we expect this value, okay? See if we can do one more here. What is it? What value is this? Minus 2 thirds. Minus 2 thirds times 7 over 11. Right? Minus 2 thirds times 7 over 11. You can figure it out, right? What's minus 2 thirds? Well, it's minus 2 thirds, right? All right, so as we pivot this number here, we want this to be 0. So to get a 1 here, we need to divide everything in equation number 1 by 3.67. That's going to give me a 1, 0, 0, 0, 0. This is minus 2 thirds divided by 3 and 2 thirds. So that's going to be 2 thirds divided by how many thirds? 11 thirds. 2 thirds divided by 11 thirds. That's 2 divided by 11, negative. So that number is going to be right here. Okay, so notice now what we have is we have x1 in the basis, we have x2 in the basis, we have x3 not in the basis. So we need to get it into the basis. So how do we get into the basis? Well, what we need to do is, what do you think we can get in the basis for us? So notice that I have all zeros here, so the only chance I can get into the basis, I have to use this as a 1 here. This is already here. So what's my objective function going to increase to? 19. So if I add this equation to this one, I'll get a 0 here, 0, 0, 0.64, negative 0.09. What do I get here? 1, and I'll get here 19. Basis, basis, basis. Now, am I done? Did I maximize the function? Well, it's telling me that what's the value of x1? The value of x1. The value of x1 is the one in this column, because notice it's got x1, no x2, so therefore this thing is equal to, we don't care what these values are, as long as they don't violate constraints. So therefore the value of x1 is 12, the value of x2 is what? 3. Is 3, and the value of x3 is 4. Got me so far? Okay, now, we're not done maximizing the function, because the reason the constraints on these numbers are non-negative means that if you ever see a number in the top row which is negative, if you can add something positive here, a part of something positive, to make it 0, then you'll add some part of something positive here, and that may increase the function. So what we're going to do is we're going to pivot. Notice that there's no hope here. There's no hope here, and there's no hope here, because basically to bring this to 0, we'd have to subtract. And that would lower the objective function. So we have no hope here. The only hope we have is only in column 7. So what we're going to do is we're going to try to bring in variable y4, the fourth slack variable, into the basis. So what choices do we have? Is this a choice? How many times this is this?
2 times.
Half, 0.5. So 0.5, and what am I doing with it? I'm adding it, right? Okay. How about this one? What do I do here?
1/3.
So, but it's not 0.5, is it? Because 0.5 of this is negative 0.09, so I need a negative 0.5. So if I did a negative 0.5 times this, I would get a 0 here, but negative 0.5 this would do what? It's negative 3/2. That would make the objective function what? 17.5. So what would that do? Lower the objective function. So I don't think it's a good idea. Now, so the other choices are, if we choose this one, for example, to put this one into the basis, that means we would have to do what here? We just add this equation to this one, so that would produce an objective function of 31. Looks pretty good. But in order for that to be correct, once we do that, we have to put this entire variable into the basis. Because right now we're assuming it's non-negative, but if it goes into the basis, we have to actually know what it is. If it actually goes into the basis and becomes negative, that's a violation of constraints, and we can't use that. Okay. So we're going to try to choose, we're going to pivot Q7, P2. So Q7, P2, 2 against 7. So now we have to find out what percentage of 64 is this, and add that percent here, add the percent here. When we do that pivot, we have raised our objective function to 22. Notice that the variables have changed. Okay, the variables have changed. The values of the variables. So that this actually maximizes the function. In fact, we know that if we get to a point where we have no values that are negative on top, the function is maximized. And so the maximum value of the function is 22. And that occurs when x1 is equal to what? x2 is equal to? And x3 is equal to? What's the value of y4? 33. What's the value of y5? Unknown. Not in the basis. How about this one? How about this one? Is this a slack variable or is this a real variable? Does it have a value?
Yes,
5. So the value of y1 is 5. The value of y4 is 33. The other values are non-negative. They're not violating constraints. So if it's not in the basis, we can assume that its value is non-negative unless it's valid. So we have maximized the function. Now I'm going to show you some problems that you can get into. And this is going to finish our discussion here. Let's go back to even our simpler value, which is our two-dimensional simplex, the same simplex, except no third dimension. So we're going to maximize only x1 plus x2. So these are the same constraints. Notice there are right now no slack variables because we have inequalities. So we're going to add the slack variables. In this case, since we have 1, 2, 3, 4 equations, we add 4 slack variables, 1 to each of them. That way we get equality, and everything is greater than or equal to 1, including the slack variables, which I forgot to put in here, but they are. So now our objective function is going to be put into our Gaussian elimination like this. So this is -1, -1, 0 across. This is our maximizing function, and we're going to try to pivot. And as we pivot, so we're going to try to pivot. In the pivoting, we're going to do P 2 P2 Q1. Let's take a look at that. P2 Q1. You understand that the 1, if we're going to pivot here, we want a 1 here. So this equation is set. So now we have to add what to here? 1. Just 1 times this. So that's going to be 0. What's this going to be? 3. What's this going to be? 0. What's this going to be? 1. 0. 0. It's 45. So the function goes up to 45, which is quite surprising. Since we know the two-dimensional simplex that we saw, there's no way we can get a 45. But what we're going to do is we're going to, in order to get this thing into the basis, we have to make sure not just get this thing here, but now we have to add 1 to here also. So that's going to give me 0. That's going to be what? 5, 1, 1, 0, 0, 50. And now we're going. Now this one is set. Don't do anything here because we already got a 1. If it was a 2 divided by 2. But this one, we're going to have to subtract what? We're going to have to subtract double of this one. So double of 1 is 2. Subtract that, you get 0. That's what we want. Double this, you're going to get negative 7, 0, negative 2, 1, 0. What are you going to get here? We're going to get a negative value here. Okay? Here, we're going to have to subtract 3 times. Let's calculate this. What is 3 times 45? 135. And what are we doing with the 135 with respect to this row? So it's 27 minus, it's 24 minus 135. That's negative 111. So as we do the computation, our matrix looks like this. Notice that we've put into the basis x1, but we also put into the basis, without trying, which one? y1. What's the value of y1? 50. How about y2? Not in the basis. How about y3? What's the value? Okay, that's a constraint violation. How about y4? In the basis? It's in the basis value of negative 111. So therefore, that move is illegal because it violates the constraints, so we cannot do it. So, so y4 greater than or equal to 0 violates that constraint. Actually, there's 2 constraints that are violated. So therefore, this 45 is false. We have to take a step back. So what I'm going to show you is I'm going to show you the proper pivoting. Again, every time you pivot, you have to make sure there's no violations. Whatever's in the basis has to fit the constraints. That's it. So here we pivot 4 and 1, and we produce this. We pivot 3 and 2, we produce this. We pivot 1 and 6, we produce this. This is a problem. Why? y2 has gone into the basis at a negative value. So we have to undo this one, go back to here, and now we're going to pivot instead of 2, 6, we're going to pivot, instead of 1, 6, we're going to pivot 2, 6. When we do that, we go to here. Now, is there any room for improvement? Is there any way we can improve the objective function? We would need to have a negative value up here to which we could add the opposite and then add something positive, but there is no negative value. Okay? Notice that here, the only column for pivoting would be this column, correct? Because of this negative value here. Notice that the only column for pivoting is right here, initially, at this spot, after the initial problem. So the initial problem is here. Initially, we could pivot here or here. And once we made the mistake, we corrected our mistake, we pivoted, that left only this one. So now we have to choose, basically, Q is chosen to be column 1, and P we have to choose. So we chose here 4, we got to this point, we chose here, for the only one, P was already frozen at Q was chosen as 6, we chose 1, but that caused a violation. It's a violation because it puts x2 into the basis, so we got to take a step back. Instead of 1, 6, we try 2, 6, and that gives us a maximized function of 18 without any ability to improve. Any questions? So this is called linear programming, and it's actually very easy to program this in a computer. And the only thing you have to worry about is the precision of the numbers. So you might have to go to a lot of precisions, and then kind of if you get like 0.999999999, you can then maybe make an assumption that this is an integer. Because sometimes you'll say it's not 0 because of the imprecision of numbers. So you have to be careful how you implement this. But I have actually a code. I don't have it with me. Well, actually, I do have it, but I'm not going to run it. But I have a code that will actually implement this algorithm in terms of code. And it's very, very efficient. And every time you make a move, you have to check to see whether you have any constraints that are violated, and is there another step to optimize. If you do things correctly, this algorithm will always lead to an optimization if there is a solution. And of course, for any simplex, there's going to be a solution. But in some cases, you may leave a simplex unbound. For example, so if you look over here, for example, what if you forgot, for instance, to have this constraint? Then basically you're allowing things to float up here, and so you will never, so basically you will never stop maximizing. You could run into a problem. Okay? So assuming that there is a visual, for a two-dimensional problem it's very easy to see. Even for a three-dimensional problem, you can generate a graph to see whether in fact you have a closed simplex. But if you don't have it closed, you could have a problem. So that's the main thing. As long as there's a closed, you're going to have a good solution. Now you understand that if I happen to have a slope of what's the slope between these 2 points here? What's the slope of this line? No answer? -2, right? -2. So slope is like, so if my objective function has a slope of -2, that means this, all of these values, right? Potentially, but look at this, 12 plus 3. But how would I get a value of -2? How would I value -2? That would be a case where y is equal to -2x plus c. So we would have 2x plus y is equal to c. What's 2 times 9? 2x plus c plus y. What's 2 times x? Plus 3. So if you're maximizing this function, which is a function 2x plus y, then you would fall essentially along anywhere here, would be a maximized value. The probability of that is relatively small, so usually the solution is going to be along one of these points. And certainly if you're going to be hitting an edge, then you can choose any point on that edge. So if you're on the edge, then any point on the edge has the same value to maximize. All right?